As we said, this has some vulnerability to a Grover search attack. So what is Grover's algorithm? So Grover's algorithm is a quantum search algorithm which can find the unique input of some black box function that produces a particular output value. So this, is really function inversion. It can find the inverse of functions. And this is important because a lot of cryptographic functions are what we call one-way functions. They're easy to compute in one direction and hard in the other, just like we saw in integer factorization. And so although the time complexity is not, we do not have as great a gains as we do with Shor's algorithm. We get a speed up of square root of n with Grover search. The applicability of Grover, I would say, is larger because cryptography uses a lot of this one-way concept in its algorithm. So we have a wide range of applicability here for Grover search. So at a high level, Grover search works using a couple of an iteration block called the Grover iteration, and this Grover iteration can be thought of as being two operations, one called the oracle, which can recognize a target solution within a superposition of the input state in a superposition of different possible candidate solutions, and then a diffusion operation, which performs a reflection about the mean, and this ends up boosting the amplitude of the target solution. So a high-level block diagram looks like this. We start on the left-hand side. We start in the zero state. Our Hadamards project us onto a superposition of all possible states, which are our candidate solutions. And we want to evaluate our candidate solutions through this Grover search. So the oracle, so in our first Grover iteration, which is this blue box here, our oracle will be some quantum operator that's defined by the nature of the problem we're trying to solve. It'll be some unitary version of a function that can recognize the solution. And it's easy to recognize a solution, just as integer factorization. If you're given P and Q, it's easy to recognize that those satisfy, a number, some given number n as the product, but it's hard to go the other way. Similarly, the oracle can recognize a solution without actually being able to find the solution itself. But anyway, within the superposition, the oracle recognizes the solution and marks it with a phase flip. We have a diffusion operator, which you don't have to know the details of this, but what it does is it performs like a reflection about the mean. So any amplitude, the amplitude values are reflected about the mean, which, as we'll see, we'll visualize this in a moment, we'll see that this ends up boosting the amplitude of our target solution. So in order to find what we want, our solution, we just implement this Grover iteration, approximately square root of n times, measure the output, and we get our target solution with high probability. So we can visualize this amplitude boosting property of Grover search on the left-hand side. So in the leftmost diagram labeled 1, our candidate solutions start in a uniform superposition. The blue bar is indicating the target solution that we're interested in. So in step 2, our oracle marks that solution and performs a phase flip. So this flips the sign of the amplitude. And then in step 3, we do our diffusion operation, which reflects this about the mean. And if you can kind of visualize this, because that flipped amplitude is going down, as we reflected about the mean, this will get boosted relative to the other amplitudes. Now, with one Grover iteration, we have maybe a marginal increase in amplitude, but as we execute multiple iterations, we can get a very significant boost in the amplitude of our target solution, and then we just make a measurement and we get the result with high probability. So how can we use this to crack our AES? So I've taken an example from a publication here that looks at the resource requirements of a quantum implementation of AES for this purpose of attacking AES. And they proposed a solution or a satisfiability function, f of k, which takes a candidate key. And essentially, if we have a set of clear text, ciphertext pairs, so M1 would be a clear text message, C1 would be the corresponding ciphertext, we can create a sort of like a Boolean satisfiability function here, where if the AES using our key, you could think of the key almost as a parameter here. using this key, if it produces the right ciphertext for each of the pairs that we have, and the caret symbol is and, it must be true for all of the ones that we have, then we know that we have the right key. So essentially, this article I've shown below, what they did was they took this idea and they implemented a unitary version of AES, and therefore, because they can do this, they can create an oracle function that can recognize the solution for when this function is satisfied. So essentially, in doing this, and the result of their analysis, we won't go into the details of that, but their conclusion was that given the number of resources, the number of gates, they feel like AES 128 is vulnerable to a quantum attack with a modest sized quantum computer.